Welcome to this presentation on integrated geophysical approach for dam health checks and monitoring and dam site investigations. I am Sanjay Rana. I am Managing Director of Parson. A brief about the company I represent. Parson is an ISO certified geophysical company. We are the largest engineering geophysics company in the country in the private sector. But more than that, we are recognized for bringing various new technologies in the country, including GPR in 1996, shear wave seismic refraction in 97, high resolution seismic tomography in 98, PST for oil exploration in 2008, and innovative use of geophysical methods for high resolution non-destructive testing of dams in 1998. Our main strength is our people who are highly experienced and trained. We have offices in Delhi, Kolkata, Bahrain, and Saudi Arabia, and Egypt and Sudan. We have agent offices, and we are working in more than 14 countries around the world. I am a professional geophysicist with 29 years of experience. I graduated from University of Roorkee, which is now IIT Roorkee, in 1990. I am a member of various working committees for development of code and practices, including IRC. And in fact, recently we have come up with a document detailing all the geophysical methods for dam safety applications also. I also have conducted various training programs, all primarily related to use of geophysics in various sectors. And my dam experience is more than 80 dams till now. So when we talk about geophysics, it's basically the art of looking into the subsurface from the surface. So just for the uninitiated, the people who have not really been involved in geophysics, I always like to start with this slide. Here you can see medical images very clearly. For example, you have ultrasound, you have X-ray, you have CT scan, you have MRI. So these images are very familiar to us. So what we are doing here is we are sending different kind of rays and waves inside the body, trying to construct the inner condition of the body, how it looks like. Now compare these images with the images here. Here, for example, you have a shear zone in otherwise good bedrock. You have reinforcement bars in a concrete slab. You have buried pipes under the road layers. You have a cavity in otherwise good sandstone. You have fracture zones here in a dam body. Now, these are the geophysical images. They also have been created by sending different kind of rays and waves inside the ground to understand the internal condition of the ground or the structure. So I always like to link it with medical imaging. That geophysics is very close to medical imaging in terms of using different kind of rays and waves and finding out the internal structure of the subsurface. Of course, there is a very big difference between the two, or rather we can say that geophysicist job is much more difficult because human body is exactly known what it is like. That the internal structure of a normal human body is known. For example, you know that there are joints here. Here you have joints, and if there is another, let's say a fracture here, that will be interpreted as a fracture and not as a normal joint. Unfortunately, there is nothing called a normal earth changes in a very short distance. So where you're sitting now, it's a different composition. You go 100 meters away, it's a different composition. So the interpretation of geophysical data is much more difficult than the medical imaging data. That's number one. Number two, human body is available for investigation in 360-degree. For example, when you are conducting this kind of a scan, the sensors are all over the head. So in from all the directions, you can send the rays and waves, and you can do the imaging of the human head here. In case of geophysics, only one surface is available for the investigation, and that is why again our job is slightly more difficult than medical imaging. Now, these are the images of dam structures constructed using geophysical methods. So, for example, here you have a concrete dam, P-wave velocity tomography has been done. You can see the low velocity zones here, which basically indicate the fracture zones in a concrete dam. This is the masonry dam. Again, it's from India. A P-wave tomography has been done. You see the low velocity zone here, which ultimately is because of regular seepage from here. and the water has carried away the fine, the material has leached out, and it has resulted in a low density. This is basically P wave velocity, this is density, and you can see how the density has reduced. This is again a dam example. This is around 470 meters from one end to the other. You can see the elevation is varying from 815 meters to around 760 meters, and you can see the low velocity zones here very clearly in this structure. So these are the kind of images which can be produced using geophysics for dam structures. Now, when we talk of geophysics as a science, it is at the intersection of geology, physics, and maths and computer science. So this is where the geophysics sits as a science. And why use geophysics? Again, if you compare it with medical science, the answer becomes very obvious. First of all, low cost is the same comparison between getting a surgery done and getting an X-ray done. Rapid coverage, you can cover hundreds and thousands of meters, and these days even kilometers in a single day. For example, if you go for airborne geophysics, you can cover a large area in a single day. It gives you continuous information. When we do drilling, it only gives us point information, discrete information. Whatever is happening in between, obviously you cannot just find out based on drilling. For example, here there's a void, there's a pinnacle in limestone, and there are fairly good chances that they will be missed if you are depending only on discrete drilling. Whereas in case of geophysics, continuous information is obtained. However, do not carry home the message that doing geophysics means elimination of drill holes. No. Geophysics is giving you physical property of subsurface. These physical properties are to be converted into geological models, for which you need certain boreholes at certain location, but it optimizes your drill holes. So for example, to do a fairly good investigation, let's say you had to do 100 drill holes. If you do a good geophysical campaign, instead of 100, you can just do 5 or 10 boreholes and still get the information which is 100 times more than the earlier information, because it is continuous. So ultimately it leads to minimization of surprises, and it should be applied at an early stage for better planning and smooth execution rather than doing it in a firefighting mode. Now coming specifically to dam investigations. When we talk about dam investigations, at present, the investigations or inspections are basically surface only. That is, people go to the dams pre-monsoon and post-monsoon, and they look at the condition of the dam. The data which is generated is extremely inspector dependent, because it depends on the motivation of the person, his knowledge, his skill set who is doing this inspection. Whether he is even motivated enough to go to the dam at the prescribed time, for example, pre-monsoon and post-monsoon. And secondly, there are no standards available for these kind of inspections. Now, there are various tools which are available for different kind of dams. For example, concrete dams, you can be interested to know the cracks and degradation, earth embankment dams for water leaks, landslides, sinkholes, masonry dams for water leaks and strength. And here are listed various tools. I'm not going to read through this table. Idea is just to show that for different kind of problems, there are different tools which are available.
Most all dams experience seepage to one degree or another. While the dam experiencing seepage may appear in sound condition, there may be damage occurring to the internal structure of the dam. If seepage flow rates appear to be increasing and the flow is not clear and is carrying material, internal erosion or piping is likely occurring. Piping is an erosion process that occurs inside the dam whenever the seepage flow starts eroding embankment materials out of and away from the dam. This starts at the downstream slope or toe and moves rapidly upstream to the impoundment. This process will tend to accelerate as the expanding larger opening or pipe allows for increased seepage flows. If left unattended, the seepage flow and progressive internal erosion will soon get out of control. When the internal pipe or void becomes large enough, the embankment structure above it will collapse. This will result in a failure of the dam's embankment and a potentially catastrophic release of the stored water, which may cause serious property damage and loss of life.
This was just one example of piping to emphasize on the point that nothing happens overnight. If there is a deficiency, like for example in a structure like dam, it takes a long time to actually a dam to fail. The point is that these deficiencies might not manifest themselves very clearly in the downstream too early. It's just like cancer. For example, sometimes we are able to detect cancer at the last stage. But if there is a regular medical checkup or regular health checkup, we are able to detect the problem at a much early stage and do the rectification. So similarly, in this particular case, the solution is timely detection. And how do we do that? So I'll go on these methods one by one. First is resistivity tomography. We also call electrical resistivity imaging. It gives vertical sections of electrical properties. It basically brings out the saturated zones in the dam body, water table, leak paths. So this is what it is used for. The basic principle of electrical resistivity is very simple. There are two electrodes which are sending the current, two electrodes which are measuring the resultant potential. Ultimately, different earth material have different resistivities based on which they can be classified. It is directly linked to the porosity. The traditional electrical method now has been replaced by electrical imaging, in which you are able to do depth-wise and lateral investigation at the same time. So this is what we call 2D imaging. This is a typical acquisition system. You put electrodes at a particular interval. It can be 1 meter, 5 meters, 10 meters, any interval, and you acquire the data. With modern system, it just takes around 20-30 minutes to acquire the data along one particular line. And this is how it looks like in terms of results. So these are the electrodes which have been put here. And once you do this complete investigation, you do a 2D electrical resistivity distribution of the subsurface. High resistivity areas will be very clear, low resistivity areas will be very clear. This is how the layout looks like in a field. This is how the layout looks like on a dam. So this is, for example, a dam where these electrodes have been put right on the crest of the dam. The readings are being taken here, and ultimately, just by around 20 to 30 minutes of recording time, you will be able to see internal distribution. This is a picture where I was taking these readings on controversial Mulla Periyar Dam. This is how we do it even on the dam which has the top asphalt or concrete. There is no problem. Small drill holes are made. The electrodes are put there. There, of course, contact is to be established using water or brine. And once you do this, you get the 2D distribution of your electrical resistivity and dam materials by themselves are basically insulators. They become conductive only when the water is there or high level of moisture is there. So this is one example of imaging sand and gravel, silty clay, how different materials are differentiated based on their resistivity. This is a real life example of a dam. It's from MP. So this dam was having a seepage problem. Seepage path was to be determined. So as you can see, this area is having very low resistivity. This area is having very low resistivity. So these two zones are clearly the zones where the resistivity is very low and they are having a very high level of water saturation. So out of the entire dam body, you are able to very clearly see which areas are having problem. One line was done a little away from there. Again, you can see these two zones are merging together almost, and this is the zone. Here you can see the depth, and here you can see the chainage. So this way you are able to see completely where exactly the problem is. This is another example of a masonry dam, very clearly showing the zone of water saturation. This is done from the dam crest. So you can see this is the distance. It's around more than 400 meters like this. This is elevation, so 810 to 720. So we are talking around 80 to 90 meters of the depth of investigation. So this is a very good example. Here is another example of a masonry dam. You are able to see very clearly the zone of water saturation, which is basically contributing to the seepage. And the zone here is just developing. It is still not so much saturated, but this still is developing. And again, these zones further can be made to look stand out for that matter in the entire dam body. So we can see very clearly which are the zones where treatment is required. Various examples of this. This was another example of a masonry dam where this zone and this zone were very clearly demarcated. This is another example where this has been merged with SP data. SP I'll be discussing shortly. So you can see the saturation. You can also see the flow across the zone. Various examples of electrical resistivity imaging. And then, of course, the results can ultimately be presented in 3 dimensions. So this is a 3D result of resistivity line. It was done to find out a cavity in otherwise good sandstone strata, and this was the cavity here. This is the cavity. This is a 60 meters by 60 meter cube. 300 meter is the length, 60 meter is the width, and 60 meter is the depth. And this cavity was actually running all along the river. You can see this cavity now here. This blue color which you see. So this was suspected during drilling, and finally imaging was done to find out this is the cavity, the complete extent of the cavity. So very powerful technique with various options to present the results. Second method which is useful for dams is streaming potential method. Streaming potential method is basically it's a potential which develops due to flow. So when water is passing through a porous material, it displaces the positive ions which are there on the membrane. Ultimately, a current starts flowing, which gives rise to a potential. This is called streaming potential. Why this is so important is that electrical resistivity imaging is giving you zones of water saturation. Now you want to identify which of these saturated zones actually are actively contributing to the flow of water, and that is where SP comes in picture. I'll show you this in an example. So for example, if this is a dam and this is a reservoir, this is the crest. So you do a one line in the reservoir area where the water is, let's say, entering the dam body, one line on the crest, and one line somewhere in downstream. So at the entry point, SP has a negative potential. Somewhere in between, it will become almost zero, and near the exit point, it will have a positive potential. So that way, you are able to completely map the seepage path. Generally, what happens is that if you see seepage here in the downstream, you assume the seepage is coming from somewhere here in the upstream, and you start all your treatment like this. That might not be the case. Seepage actually might be taking a path here. So it's important to understand this path. Similarly, if the seepage is taking place from the reservoir floor, that also can be detected using SP. We also have mastered the art of doing SP on dams with concrete floor, top or asphalt top. This is a very good example of how the SP result is interpreted along with the. So this is a beautiful example of integrated interpretation of electrical resistivity imaging and SP result. This was done on a masonry dam. You can see it was a very long dam. It's 2.6 kilometers. It's a very big dam. And there was a seepage being observed in this dam in downstream somewhere here. And they wanted to know where exactly the seepage is coming from. So electrical resistivity imaging was done, and you can see the low resistivity zone here. You can see a low resistivity zone here. You can see a low resistivity zone here and low resistivity zone here. But when the SP was conducted, it became very clear that most of the SP development is taking place from this zone. That is, this is the zone which is actively contributing to the seepage, whereas these three zones, there is no SP development. So these are basically still dormant as far as seepage is concerned. But if you are planning to do treatment of this dam, it is prudent to treat all the four zones, because very soon, maybe in the coming 4 to 5 years, these zones also will become active conduit of seepage. So this is how the interpretation is done together of SP and electrical resistivity imaging. Various example of for example, you have a low resistivity zone here, 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 but this is the zone where negative SP development is taking place, clearly showing that this is where the seepage is taking place, whereas these are just saturated but not contributing to active seepage as of now. GPR is another very strong method for near subsurface investigation. It basically works on the principle of electromagnetic reflection, EM reflection. It has a transmitter and a receiver. Transmitter is sending EM impulses into the ground, which are getting reflected from wherever there is contrast in dielectric constant. And we are recording this reflected pulse. Ultimately, you get images of the subsurface like this. So for example, this is a buried pipe under the layers of road, and you can find the depth based on dielectric constant of the subsurface. Equipment these days is very handy. It can be carried by a single person, and investigation can be done very, very fast. This is how a cavity will look like on a GPR record. So for example, if you're working on concrete dams and you're looking at near surface things like cavities, cracks, extension of cracks, it's very interesting. This is from a dam in Kota Barrage, where this zone was detected using GPR. It also can be used for the reservoir studies to find out the various layers of sediments in the reservoir water. This is the same GPR in the tomography mode between two boreholes. So this was upstream borehole and downstream borehole. Ultimately, GPR result was converted to volumetric percentage. You can see the percentage water here, 2 to 38. And very clearly, this is the zone of water accumulation in the dam body. And this is how it is. This is how it is coming. Very interesting result from GPR tomography. This is a real life pictures. This is on the dam top. This is a 38 megahertz antenna going pretty deep. This is 300 megahertz antenna for shallow investigation. When I say deep, it can go to 35-40 meters, sometime more depending on conductivity of soil. This will be 4 to 5 meters. And you see, this is how here bedrock is very clearly visible in this particular case. This is a bedrock line. You can see dipping shallow bedrock interface here. You can see a cavity in the dam body, and the depth here is around 17 meters. These are depth scale, these are distance scale. Seismic refraction, a traditional seismic refraction tomography based on this is a source. For example, you send the seismic waves inside the ground, they get refracted when velocity of V2 is more than V1. There is a critical refraction that takes place, ultimately recorded on the geophones. I'll not go in the theory, but ultimately once you do this and you're using geophones as the sensors, you record the data, and once you process this, ultimately what you get is p wave velocity distribution in the subsurface. So this is, for example, elevation 0 to 30 meters. So this is the topsoil, this is the interface of topsoil and weathered bedrock, and this is very hard bedrock. This is the velocity scale. So you're very quickly able to get the p wave velocity distribution. This is for a dam site investigation. We are able to see very clearly how the rock line is going, where the rock has gone deeper, and this is how you get the results of seismic refraction tomography. Velocity models, this is how you obtain them. And see, the advantage is that this is a very small shear zone. This is hardly 7 to 10 meters, and it is 0.0001% chances that you'll be able to detect such small zones just by regular drilling. But these zones can become a big problem if you are constructing a project like dam or a sensitive engineering project, and they can be detected very quickly and accurately using seismic refraction tomography, which is of course different from traditional seismic refraction, which gave only layered based models. So it gives you bedrock profile, rock quality and depth, thickness of overburden, fracture and weak zones, slope stability studies. And in dam, it is very good to do refraction tomography to understand the foundation condition. For example, here this is the rock line under the dam, and you can see this is where the velocity lowering is taking place, and this is where the problem is. So we are able to do these kind of studies using seismic refraction. We also can find a phreatic surface in the dam body, saturated zones and unsaturated zone. The phreatic surface line is very important at times to determine. This is how you can determine it using seismic refraction.
One of the most serious dam safety concerns is the stability of the earthen embankment. Unsafe conditions could lead to a major slide that threatens the safety of the dam. A key factor to stability is the location of the phreatic line, or the fully saturated zone of the soils within the embankment. In safe dams, this level is well confined below the surface. Since soils that are fully saturated are not as strong, a higher phreatic line can reduce the ability of the embankment to resist sliding. This is often noted by seepage exiting on the downstream face of the dam. Weak or poorly compacted soils can increase both seepage and the phreatic level, as well as weaken the embankment, contributing to a sliding failure of the dam. Properly designed dams often include an internal drainage system, such as a sand chimney and blanket drain. They serve as a filter to keep seepage from moving any soil, as well as allowing seepage to be removed in a controlled fashion. This lowers the phreatic line and improves the stability of the embankment. For existing dams with a high phreatic line, two alternatives can improve the dam's stability. One is to add a drain near the toe to both filter the seepage and lower the phreatic line through a controlled release of the seepage. The second is to add a berm for added resistance and improved stability of the embankment. This does not lower the phreatic line, but improves the dam stability by adding weight to prevent slides in the embankment.
So this is the importance of understanding the phreatic line. Remy, or refraction microtremor, or MASW, is the method to understand the shear wave velocity distribution in the dam body. So this is one example of Remy, which was done in a dam in Maharashtra. This is 100 meters depth, and you can see here this is a zone where the shear wave velocity is very, very low. So out of this entire masonry portion, this is the rock line, of course. This is a rock line, and this is a masonry portion. Here a lot of deterioration has taken place, which becomes very, very clear from these results. Similarly, you can see the results here also, the weak zones, that is of the low velocity. Here you can see this is the weak zone, the low velocity zone. So this also is a very quick method to understand the shear wave velocity pattern inside the dam body. Here you can see the zones, the blocks from where a lot of leaching has taken place, resulting in low velocity zones here. Seismic tomography is one of the most advanced methods, most high resolution method of dam investigation. It gives you acoustic wave travel times, properties of each cell, gives you color tomogram of the dam, help find weathered concrete fractures, and highly detailed information. So till now, whatever methods we have discussed, we were using from the surface of the dam. In this particular case, we are doing it either between the boreholes or between the two faces of the dam. So this is the various sources to generate the seismic waves: a hammer, a nail gun. So this is the basic configuration. You have sources and you have receivers. So this is the upstream, this is the downstream. You can have it either way. You can have sources here, receivers here, or the other way around. Idea is to have a crisscross of the entire dam body by these ray paths. So this is basically, this is the crest, sources on the crest, receivers here, sources here. As I said, any configuration till the time you are able to generate a good crisscross of receivers and sources. So this is, for example, a dam. So you're taking a cross section. So one line is here, and if this is upstream and downstream, so we put the sensors on the upstream, or the source on the upstream, and the receiver on the other side. So the installation of accelerometer on the upstream phase. This is accelerometers mounted on the upstream phase here, or in the reservoir area we can put the hydrophone string. So you don't need to empty the reservoir. It can be done in the full reservoir. You can either use the hydrophone in the upstream, or we can use source using a sparker. So a sparker is the source, or hydrophone is the receiver in the upstream. And this is the using the nail gun seismic source on the downstream. Instead of nail gun, we can also use a sledgehammer. Idea is to generate seismic wave here and record it on the upstream side. And these are the results. So this is a concrete dam. This is a downstream wall, the upstream wall, and these are P wave velocity. So 2100 to 4400. All this is acceptable quality of concrete, what you see in yellow and red. But when you are going to this zone, that is around 2500, 2400, this is basically the fracture zones in the concrete. So very beautiful, you can say, MRI of a concrete dam. Similarly, this is a picture from a masonry dam from India. You are able to see the high velocity zone. These are high velocity zones, and you are able to see the low velocity zones. So this was done on the spillway. So these are the lines on the spillway where this was done. And you see the results here. These are the low velocity zones. So this is velocity tomography, which is converted to density tomography using Gardner equation. So you can see the density in these zones have come down to around 1.8 to 2, whereas in the remaining dam body it is in the 2.6 or 2.7. So this is the zone from where a lot of leaching has taken place, and the density void has been created. Now the beauty of this technique is that based on these results, you can actually estimate the amount of grout that will be required for rehabilitation of the dam. This is the shoulder section. Again, you can see this is the low velocity zone. Here is the low velocity area here. So low density area. So you're able to calculate the volume. This is the cross section. Same thing you have in the L section, so you can calculate the volume. This is how we do the L section. So geophones in the gallery is striking on the top, recording the data, and finding out the properties of the complete dam body between the gallery and the dam top. So this is, I'll show you some example from dams in India. This is the longitudinal main line, and these are the sections which we did. So the hammer source for longitudinal section is Sparker Pro for impulse generator. This is geophone. These 360-degree geophones for at the top of the dam's gallery. This is drilling the hole for putting the accelerometers in the upstream. This is hammer to generate the source. This is the configuration. This was done upstream hammer. Here it was Sparker under the water level, and here the accelerometers were put. And these are geophones in the gallery. Here are the strike on the spillway. And this is the ray paths which were generated doing the L section of the dam. And this is how the L section looks like. So this is around 430, 450 meters of dam length. This is the gallery. This is the dam top. And by doing this L section tomography, we are able to see very clearly which are the zones of less P wave velocity. That is basically the weak zones. Very, very clear. And then across these weak zones, we will plan our cross sections so we can actually kind of create a 3D model. So these cross sections were done across them, and this was on the other dam, the smaller dam, again very clearly which are this was a spillway section, very clearly which are the weak zones. This is the result superimposed on a dam drawing. Gallery, dam top, spillway, entire dam body has been x-rayed. And these are the cross sections. Again, clearly showing the zones of low velocity and low density. So then we integrate the data, resistivity image for depth and saturation, SP for flow, georadar for voids and cavities, georadar for interfaces, tomography for material properties. And this is one example where one line was done in upstream, one on the crest, and 3 lines in the downstream of SP and resistivity, and they were linked together to make these seepage paths. All right, so the next big question is that since I've discussed so many techniques, which is the technique or tool which is right for a particular dam? So it depends on objective of investigation, the resolution required, the depth penetration required, the physical property to be defined, geometry of the dam, and nature of the target and host material. It's very important to choose the right method for the right work. Sorry. Now you can also do stilling basing concrete degradation studies using these methods. This is one very quick example. Now this continuous impact of water may lead to scouring and erosion of floor over a period of time, and generally they are full of water here. So this was a GPR which was done. Sorry, this is the floor of the stilling basin. Good, no problem here. Depth here you can see is around 5 meters. Around 10 meters depth, and here is the deteriorated zone. Here is the eroded zone, deteriorated zone, eroded zone, and this is the depth of the water. So this can be done when the water is there in the stilling basin, and very quickly we can do the investigation of the stilling basin. And this was combined with bathymetry. You can see these are the zones of problem here. When these investigations should be done? Well, if you're waiting for a sign, this is it. A dam investigation should be done right after completion of a dam to have a baseline data. For older dams, this time is now. Before designing a rehabilitation plan, after carrying out rehabilitation work, changes in physical properties are much easier to interpret than one-time measurement values. So under normal conditions, such measurements should be repeated every couple of years as a routine dam inspection program. And last topic, advanced geophysics for dam site investigation. So things like refraction tomography, imaging, and Remy can also be used for your dam site investigation. This is one example of refraction tomography for dam site. You are able to see very clearly where your rock is. If there is any problem in the bedrock in terms of shear zones, you are able to pick these up. You're able to pick up the cavities, if any. You're able to see even the soft zones under the rock cover. Very good example from Lahaul Spiti Valley. It can also be done across the flowing rivers. where doing drilling is a big problem, but you can across the flowing rivers in a day. We have covered around 450-meter width of the river and found the bedrock profile there. So both seismic refraction tomography and ERI can be done in the flowing rivers, giving you the complete bedrock line here, the bedrock line here, is the river water. So finally, these are the most suitable methods for regular health check of dams for early detection of problem. They are totally non-destructive, help design rehabilitation programs better and accurately, helps assess success of rehabilitation measures undertaken, identification of damaged areas inside the body of the dam, identification of not visible fractures and voids, and zones of seepages. So more information at low cost and very quickly.